It is my pleasure to introduce our presenter. Today we have instructor Jeanette Shutay from the University of Chicago speaking on supply chains and the triple bottom line. Jeanette, the mic is yours.
Great. Thank you, Jose. Hello, everyone. I'm so glad that you decided to join us this evening. I will be talking about, obviously, supply chains and the triple bottom line. And just to give you a little bit of a background, I have a PhD in research methodology with a statistics specialization. And coming out of grad school many years ago, I ended up going into forecasting and demand planning. And so I have 15 plus years in supply chain analytics and marketing analytics, as well as logistics experience. And then I also teach supply chain optimization and time series analysis and forecasting at the University of Chicago. I own and run my own consulting practice where I've done quite a bit of work around program evaluation. So it's a little bit of a different flavor than supply chain analytics. And then I've recently taken a role as a director of AI consulting for EPAM systems. So I'm a busy person. And I am going to accept questions throughout the presentation. So feel free to raise your hand. I believe Jose will be moderating that. Is that correct, Jose? Yeah, okay. So feel free to raise your hand.
Sorry.
Thank you. And then we'll also provide 10 or 15 minutes at the end for questions as well. So without further ado, I will go ahead and get started. I want to make sure everybody, can you see my screen in the presentation? All right. So the problem today, for those of you, most of you probably don't know me very well. So just to give you a little bit of background about what I'm passionate about as it relates to supply chain is, well, just in general, really, is optimizing the triple bottom line. So from a supply chain perspective, we're focusing on people, planet, and profit, right? And so how do we incorporate the triple bottom line into the supply chain systems that we are and the challenges that we experience today? So as you all know, supply chains are obviously critical to our livelihoods. We depend on it for medication, we depend on it for food, we depend on it for all kinds of things. So we absolutely need to rely on supply chains for our day-to-day living. However, with the current state of affairs, supply chains are particularly vulnerable, and they're vulnerable for two reasons. One is increasing operational costs, and that is primarily due to operational inefficiencies, but also waste. There is a significant amount of waste within the supply chain systems, and that permeates across a lot of different supply chains, not just food, but within pharma, within retail, CPG, cosmetics, whatever it may be. So because of a lot of the ESG, it's becoming more and more prevalent and more popular for people to start thinking about ESGs and the environment and in sustainability, which is obviously a good thing. That is contributing to this increasing pressure for supply chains to be environmentally friendly. And unfortunately, a lot of those, the procurement and the in order to fulfill a lot of the consumer demands that we have today, it leads to a significant amount of deforestation. And as you probably know, deforestation has a significant impact on our ecosystems, biodiversity, as well as climate change. But also, obviously, if we're supplying more than we actually need, then we are harming the environment, more than we need to harm the environment to sustain our well-being. But also we're producing waste, and waste goes into landfills. And as you can see, the problem of waste just becomes even more problematic. So given the fact that the second challenge of being environmentally conscious compounds the first challenge of cost, right? So what do we have to do from a supply chain perspective to reduce harm on the environment? And again, that's just going to increase cost to the system. So they kind of, they go together, and it just increases the challenges that the supply chains face today. Going to the next slide. So what should our main focus be? In my opinion, waste, as I mentioned, there's operational efficiencies and there's waste. Operational efficiencies can be managed through a lot of different areas, right? It could be route optimization, network optimization, a lot of different ways that we can think about how do we make the supply chain more efficient. I'm going to focus specifically on waste for the conversation today. And that is because waste is, I think, the area where we have a lot of control, where we can have a significant impact and reduce waste. And obviously, as I mentioned before, waste has such a significant impact on the environment. As much as 38% of the food that we generate today through a supply chain is wasted. Think about that. So that is huge. That's a huge opportunity. And as I mentioned, deforestation is a problem, and that, as we have agricultural demands, that just increases the problem even further. So in my opinion, finding ways to reduce food waste should be a priority for all food supply chains. So if you haven't kind of figured it out yet, I'm focusing specifically on food supply chains for this conversation. And how do we optimize the supply chain to minimize waste and maximize profit, to be very specific. So we need to select a forecast approach to optimize our supply planning. And you might ask, what are the things that we need to consider when we start to think about selecting an approach? So it starts with the demand forecast. What is the demand? And then how do we translate that demand to a supply plan? So some of the most critical questions that we have to ask ourselves and we need to address before we think about what approach we want to take and what strategy we want to employ, we have to figure out, is this, what exactly are we dealing with? Are we forecasting, are we creating a demand and a supply plan for a new product introduction? Because those behave very differently, and we take a very different approach if this is a new product versus something that has historical sales, for example. Is this a product that's heavily promoted? Is this product highly seasonal? Is it a slow moving product, or does it have intermittent sales? Are the sales highly stochastic or variable? And how much usable history do we have today to use to generate a forecast? Those first 6 pertain mostly to the demand plan. 7 through 10 pertain more to the supply plan. And those types of questions revolve around, do we have a short shelf life? With food, obviously, there's a lot of items that are going to have a short shelf life, like produce. Are inventory levels severely constrained due to holding costs or available storage space? So for example, if we try to err on the side of not oversupplying, we may supply very little up front. And then if demand comes in higher than expected, how quickly can we get that supply into holding? And if we can hold supply, what does it cost to do that? Are the case pack sizes optimal? So if you have, for example, if your demand is 40 units per week, but your minimum case pack size is 100, that's not very optimal. You're going to have way more than you need just because your case pack size is too large. So we have to optimize case pack sizes as well. And are we working with a multi-tiered complex supplier network? I'm not going to really get into that too much because that's kind of outside of the scope of this presentation. But multi-tiered supplier networks are going to make it a lot more difficult to orchestrate across all of the different components of a supply chain. And with that said, I also want to highlight the fact that what I'm talking about today in terms of demand planning and supply planning is just one component of the supply chain system. And the system is very complex. So I'm just focusing on one component of it. So what are the components of a forecast? At a very basic level, we talk about baseline, promotional impacts, and external factors. So baseline sales, the way that I'm defining them for today's presentation is whatever the trend is. The trend could be an inclining trend, a declining trend. There could be no trend. It could be a flat line. So sales are constant all the time. So baseline is your trend plus your seasonality. It strips away all promotional activity and external factors to the best of our ability. So for example, If there are weather impacts, we want to remove that from the baseline. If there are competitor impacts, if McDonald's is doing a promotion and Burger King is doing a promotion across the street, what impact does Burger King's promotion have on McDonald's sales, right? So we want to be able to really try to tease out all factors that are promotionally or externally driven, and just focus on baseline sales, which is trend and seasonality. There are some challenges to that, because products that have no history, like brand new products that are entering into a market, or products that are constantly promoted, like Happy Meal toys in a McDonald's system, for example, they don't have true baseline sales. We don't know what baseline is, because there's either no history to determine what a baseline is, or they're always promoted. So we don't know what their sales would be like if they weren't promoted, right? So in those examples, I'm going to talk about that in a minute. But in those examples, you would use quasi baselines. So we have, again, baseline sales is the core component, and then we have promotion related baseline sales, and then how do related impacts affect the baseline? If we have items that are promoted, what does the promotion have? What effects does the promotion have on the promoted items? To what extent is it going to increase the demand? For non-promoted items, are there halo or cannibalization effects? Those are incredibly important estimates that we want to generate, that we want to predict, because when you think about a supply plan, keep in mind that it's not just one item that we're supplying for. So for example, in a food supply chain, if you're promoting a particular sandwich or burger, there are items that are shared with there are core items like a pickle, a bun, lettuce, that are shared with other items. So we really truly need to understand how not only that item is affected by a given promotion, but how other items on the menu are also impacted, so that we can get the best view of demand for the entire supply chain. We have external factors, as I mentioned earlier. Are there weather impacts? Are there competitor impacts? Are there local events that are occurring that might affect sales? And then if you look to the right, you can see an example. This is actual data. It's from a Kaggle data set. This is an example where you have an item that is fairly commonly promoted. So you can see the pink bars are the discount, the extent to which there's a discount. And then you have the actual sales that are in black and the forecasted sales that are in blue. As you can see, as the discount the percent discount increases, the sales spike, which is intuitively correct, right? We would expect that to happen. I have a slide in the appendix, and I can share this deck with University of Chicago, or with folks if you're interested. But there is a slide in the appendix that does a little bit of a deeper dive on this. And as you can see, the forecast does not assume the full peak during the peak part of the promotion, but it assumes that the sales continue outside of that, outside of the actual peak. There are two reasons why this might happen. One is a break in supply. So it may be that we forecasted that there would be sales that are kind of flatlining into the next couple of weeks of the promotion, but that could be because the first week or the second week of the promotion, we broke supply. And so sales actually came down, but it's not because of demand, it's because of supply. So sometimes we know that's the cause, sometimes we don't. A second reason why sales might actually decline like they did in this example within the third week of the promotion could be because of promotional fatigue. Folks have gone, they're no longer interested in the promotion. It's kind of old news. So those are kind of two reasons why we might see that high spike. It looks like it's week 2, and then kind of dropping down after that. So obviously having data that informs us, was this a break in supply or not? It's pretty important. It's a break in supply. obviously we're gonna respond to that situation differently than if it's consumer or promotional fatigue. So handling continuously promoted items, as I mentioned, when you have items that are constantly promoted, we don't know what their baseline sales are because they're never not promoted. It's never a baseline situation. So in those cases, we might look at a decomposition model where we're just teasing apart trend, seasonality, and noise. So as you can see in this particular visual, you have your observed series, which are your actual sales at the top. A decomposition is a quick and dirty way to pull out the trend, the seasonality component, and the residuals, which is your noise or your unexplained variability, your, the part of the series that's unexplained. And so when you think about trend plus seasonality, like I mentioned before, if you take the two of those and you add the seasonality to the trend, that's what I'm calling a baseline. In this particular situation, if it's continuously promoted, we're calling, again, a quasi baseline. And what you're looking at here is, what is your deviation from your typical performing promotion, right? We don't know what life looks like without a promotion because there's always a promotion. But we can say, what does your typical promotion look like? Or what do your sales look like under a typical promotion? When we tease apart these components and we're left with the residual or the unexplained, we could use that as our target variable. And then we can take the promotions and we can model those using, a regression model, a GBRT model, and any kind of XGBoost model. And we can say, to what extent do those promotional features explain the unexplained, right? How do they explain the deviations from the quasi baseline? And then that gives us estimates of promotional impacts. So for example, if there's a promotion whose coefficient or whose impact is 0, then it performs like an average promotion. If you have a promotion who generates a positive impact to the quasi baseline, then it performs above or better than an average performing promotion, and so forth. So you get the general idea there. And that allows us to then use those promo impact estimates to predict what we could expect to happen in the future. So guiding principles when you're trying to forecast demand. I'm going to say this over and over and over again. One of the best ways to improve your demand plan is to get better data. Sometimes that's more data. Sometimes it's the data you already have, but improving quality. And sometimes it's create your feature engineering. For example, if you're looking at weather impacts, it may not be the actual weather itself that explains deviations from forecast. You might have an unseasonably warm day or an unseasonably cold day, which could affect, ice cream sales, for example. It may be the change from one day to the next. And I actually found that in some of the work that I've done. So if I say, what is the temperature to yesterday and did that affect sales? It may not. But if I say, what was the change from the day before yesterday and yesterday? And if the change was significant, it was significantly colder yesterday than it was the day before, or significantly warmer, that actually explained deviations from forecast more than the actual weather itself. So those are some things to start thinking about. How can you be creative in your feature engineering? How can you take the data you currently have and create new data without actually going out and buying data? So that's one thing. The second is to actually go out and do proof of concepts with data vendors to see if the data actually improves your forecasting capability and gives you a better signal. If it doesn't in the POC, then you don't want to spend the money on the data. But that's the first place to start. And when you're looking at experimenting with data, you want to hold your algorithm or your models constant because you don't want to muddy the water. You want to look at what is the pure impact of the data on the accuracy without confounding it with changing the algorithm. So whatever your benchmark model is, you would use that benchmark model and you would experiment with the data and manipulate that. And then you would say, okay, I think I know what is the best way, or which data sources are the most predictive, and which features are, give us the biggest bang for our buck. Once you figure that out, then the next step would be, okay, now let's see if we can improve our performance by changing the model of the algorithm. And then once you do that, the next step is, okay, can I hyperparameter tune to get a better result? And you might actually want to do the hyperparameter tuning while you're still doing the bake-off of the algorithms themselves, because sometimes you might tune a hyperparameter tune and get a better result from one model than you would have if you didn't. So you can hyperparameter tune while you're having competing algorithms or models, or you can compete, do a leaderboard with the models first without doing the hyperparameter tuning, pick your best algorithm or model, and then hyperparameter tune that. It's a personal choice. Historically, the models that people have used have been state-space traditional time series models like ARIMA, exponential smoothing, auto regression models. Those are models that, and Ceramax, Serema models with exogenous regressors. Those are traditional models, statistical models that we have used historically. As you'll know, and I don't know if I'm saying this correctly, but it's I can't even say it. It's a Greek name, Makridis et al. In 2022, and I could provide the citation and the full reference for that later. They initially did a paper where they competed the traditional statistical models with the machine learning models. They did a competition and they looked at different scenarios, and that was in 2018. And then in 2022, they revisited the problem, and they found that in many cases, the machine learning and even some of the deep learning models outperformed the traditional statistical models. And so one of the things that we want to think about is, let's balance the accuracy with the complexity and the interpretability. So does it make sense to go with a more accurate model if it's more complex, if it requires more compute, if it has a higher latency, if it's less interpretable? How do we make that decision? How do we balance those trade-offs? So again, we want to think about, is the simpler model a better choice, even if it's not as accurate? And I'm going to give you some examples why a simpler model may be better, even if it's not as accurate. The one is obviously, they're easier to interpret and manage. They generate fewer carbon emissions. And that's going back to the whole, planet piece of it too. We want to do as little damage, minimize any damage that we can do to the environment. There are ways that you can kind of use virtual VMs that leverage renewable energy. I actually have solar panels on my roof. So if I'm using my local computer, I might do most of my compute during the day when the sun is, the brightest or the strongest. So there are ways around that, but in general, carbon, the AI movement has a significant carbon footprint. So just be cognizant of that. Other reasons why using a simpler model or even a single model architecture is advantageous is because if you use a single model architecture, you're going to have a simplified workflow, which makes maintaining those models a lot easier. And it also is going to make debugging a lot easier. You're also going to have a consistent set of performance metrics. So again, it makes model monitoring easier. I already mentioned lower compute costs and faster model training and deployment. It's easier to integrate a single model architecture into your workflow and systems. You also have uniformity in prediction. So your forecasts don't have large swings over time, from 1 week to the next. This is critically important. I'm going to give you an example where this was a primary driving force in the decisions I made at a company I worked at, where we went with a less accurate model simply because it did not have large changes in our forecast. So if we were to forecast 4 weeks out and then a week later, we refreshed those forecasts, our forecasts would not change significantly unless there was a good reason, like we had new information that they're going to do some promotion. Obviously, yes, then we want to include that. But if your inputs and your assumptions don't change and you forecast 4 weeks out, and then a week later you refresh those forecasts and they change significantly, you're going to have a really hard time explaining that to your client. And you may have a hard time explaining that to yourself as well. So that's something to take into consideration. And then finally, simpler models have a lower likelihood of overfitting. Okay, those are some guiding principles for thinking about how you might want to approach forecasting demand. So how do we put this into practice? I'm going to give you a practical example where I'm going to take you through the demand and the supply plan, where we actually make a decision about which model to select and what approach to take. The very first thing you want to do when you're deciding what approach to take is to assess the potential economic benefits of it. So if you're hired to improve your forecast accuracy, let's say you're hired as a data scientist to reduce waste and increase profit, you're going to, if you reduce waste, you'll inherently reduce the costs, which generates healthier margins, right? But before you get started and you say, okay, what are we going to do and how are we going to do it? You need to assess what is the return on your investment. So the first thing you want to do is you want to think about how much do we actually need to improve our forecast accuracy to achieve, let's say, a 1%, 3%, or 5% increase in profit margin. You can do that by simulations, translating that into an economic return. So here's an example where if you look to the right, a 1% accuracy improvement might not change your profit at all. You might say, well, how could that be? Wouldn't we get some benefit, financial benefit from that? Well, not necessarily, because you have to factor in the costs of the improvement. How much money are you spending to make that 1% improvement? How much time are you putting into that effort? How much are you paying your data scientist or data scientists to do that? How much is it going to take from a technology standpoint to get that deployed? All of that factors in. But even let's say that there is no cost associated with building this out, which there always will be, but let's just say there isn't. You still might not see an improvement, because if you're saying that, for example, your 1% improvement might not change the actual supply chain decision you make. If your case pack size is 100 and your demand is 100, you're forecasting 98. A 1% improvement gets you to 99. At the end of the day, you're still supplying 100. So the actual decision of what you supplied didn't change at all, even though your forecast went from 98 to 99, and now you're only 1% off from what the true demand is of 100, right? So those are the types of things you have to think about. How does this actually translate to profit? You can't just look at how much more accurate is your model. You got to look at so many other things. You got to look at, are you over or under forecasting? Do you have a bias? You have to look at case pack size. You have to look at the cost of implementing. So we definitely want to consider all of those factors before we decide whether or not it even makes sense to try to do the improvement. Are we going to expect a return? All right, so you have an economic model that supports your initiative. The juice is worth the squeeze based off of your simulations. So now what do? Now you do a proof of concept. You actually assess the feasibility through a proof of concept. So you need to prove that you actually can make it better. You're saying, if we make it better, we should expect this return. Okay, well, can you make it better? We don't know. We've got to do a POC. Typically, POCs run for about 12 weeks, 6 2-week sprints if you're using an agile methodology. But some POCs can be as short as 3 to 4 weeks. It just depends. Usually they're not more than about 12 to 13 weeks tops. If you're doing the POC and it's successful, the next step would be to do A/B testing to assess the operational feasibility and the economic returns in the wild. Because what you do in a lab environment with static data is never going to translate in production. So you want to say, okay, we've done this in a lab. We've managed to prove that we can increase our model accuracy by whatever percentage you needed to increase it by to get the economic return. Now let's see if this works in the wild. And then if the POC is not, if once you put the POC in an A/B test, if it's not successful in an A/B test, then you need to reconsider your approach or you move on to a different use case. If the A/B test is successful, then we would want to scale it and put it into production, right? Pardon the Cubs celebration, but I don't know that I'll ever see another World Series win by the Cubs. So I put that in there because I just felt like it. But we celebrate. We have a success. All right. So let's go back to, so we've done an economic assessment. We proved out that the juice is worth the squeeze. We've done a POC, and now here are our results. What do we do? How do we take these results and act on them? All right, so let's assume for a minute that we have four different items, and this is real data. Again, this is a Kaggle data set, but there's 4 items, and they have different attributes. So one item has high variability, one item is a low volume item, one item is a low variability item, and the other one is a high volume item. And we have 4 different algorithms or models that we're looking at, and we're seeing which model performs best under which circumstance. Does a particular model outperform another one in a high variability situation? Now, the national and regional is a top-down versus bottoms-up approach. And I'm not going to get into that in this conversation, but that's another thing that you want to think about from a forecasting strategy is, are you doing a national forecast and then sharing it out to the individual locations or regions, or are you doing it at a location or region level and then rolling it up to a national level? Again, out of scope for this conversation, but that's definitely something you'd want to consider. So if you look at the results in the chart, we can see that regional models outperformed the top-down approach in most cases. We see that error is greater for stochastic items and for low volume items, which is to be expected. If it's a low volume item or it has intermittent sales, it's going to be harder to forecast. All other things being held constant, that's just a fact. If it's got a lot of variability, it's stochastic, it's going to be harder to forecast. Your heavily promoted items are going to be super hard to forecast. We see that differences in performance between models was smaller for low variability and high volume items. So it's not only good enough to look at the MAPE, the error, you also want to look at the variability around that error. What is the standard error around your error? Or what is the standard deviation around that error? You want to see a small error bar because you don't want to forecast a model that forecasts, let's say one model has a 26% MAPE and another one has a 28% MAPE. You might want to, that's a mean absolute percent error. That's a common metric for forecasting, by the way, mean absolute percent error. That's what a MAPE is. And that's a common metric that we use to assess forecast, the quality of a forecast. So let's say you have a 26% MAPE, so 26% error on average, and you have a 28% MAPE. You would say, all other things being held constant, go with the model that gives you the 26%. But what if the model with the 26% has some fairly significant outliers, error outliers, like it really grossly misses the boat on some forecast, but the rest are really, really good. And then you have the 28% that doesn't have these extreme errors. It's more consistent in the errors, but it's not quite as good. You might want to go with a higher MAPE that has a smaller error band, because these big misses are much more difficult to bounce back from. A supply chain can bounce back from, and they can be pretty resilient to errors. But when they're extreme, it's very difficult to overcome, to be resilient when you have significant misses. So I want to really hit that point. Okay, you want to make sure that you're looking at not just what is the overall average error, but what is the distribution of the errors as well. So do we have enough information to move forward with a specific model? No, we don't, because even though these models are helpful, they don't give us all the information we need to know. We need to know, do some of these models over versus under forecast? Do they have an over or under forecast bias? And if so, by how much? We also need to consider some of these supply chain factors, which is case pack size, shelf life, and other constraints that we may have. Sometimes we have, we have lead time constraints. So once we incorporate those factors into our plan, we can better understand which model is superior. So let's do a deeper dive into one of the items. Let's look at the high variability item and see how this process works. So on the right, I have an example of stranding. So this is where, let's assume the case pack size is 60. This is a fish item. They're all food items that we were looking at in that chart that showed the MAPEs. They're all food items, but I picked the one that had the most variability, that was the most stochastic. And if we assume a case pack size of 60, if we say that's what we have to work with, and we look at the extent to which it over versus under forecast. If we compare, let's say, for example, the XG Boost model is our benchmark. Let's say that's the model that's currently in production today. We want to compare the GBRT model to that, the gradient boosting regression tree model. We have to look at, again, all of those factors. We can't just look at accuracy. So the visual on the right compares the models on stranding. So if there's positive values, that means that they had stranding, it was over forecasted. If there's breaks in supply, that's the negatives. That means they ran out, right? Now running out is a problem too, because if you run out, that could be lost sales, because sometimes people will not buy something else. If they came for that particular item and you don't have it, they may not switch to a different item, or they may switch to an item that's cheaper. So there's money to be lost in breaks in supply. So you don't want breaks in supply either, okay? If we consider that GBRT had a forecast error of 26.2% and the XG Boost was 31%, the difference is about 5%. What does that 5% translate to when we look at it from a cost perspective? If we assume that the price of the item is $10 and the food and paper cost is 30%, if we assume that we lose 50% of the sales, you could read, I won't read all this to you, but basically at the end of the day, what we see is that the GBRT model, that 5% accuracy for this model, when we factor in case pack size, we factor in forecast bias and all of that, we would expect a 26% increase in profit and a 9% decrease in waste. These are, numbers that are based off of a lot of assumptions. You cannot necessarily expect that a 5% MAPE improvement is going to translate to these types of numbers. Again, it depends on all those other factors that I've been discussing. So I don't know about you, but I'm looking at this and I'm saying, let's go with the GBRT model, because it definitely gives us the reward that we're looking for. Now, finally, the last thing to consider is, what does it cost to deploy this? What does it cost to get the team to deploy this? What does it cost to run and operate? We have to, maintain the models. We have to think about model drift, data drift, which you would probably have to be doing with your XG Boost benchmark model anyway, so it shouldn't be too much from an incremental cost perspective. You have to think about your runway. You may actually be spending a little bit more upfront in your first 6 to 12 months, but over 3 to 5 years, you could be significantly improving your ROI. So in conclusion, Supply chains must place a greater emphasis on triple bottom line. They need to do it for their brand because people care about this. This is becoming more and more of a concern of the general public and the consumer. And we have to, because we're in a crisis right now with deforestation and biodiversity loss. Making supply chains more environmentally friendly will invariably add costs to the chain, but we can offset those costs by optimizing the chain and mitigating those risks. One of the most powerful ways to reduce the negative effects of the supply chain on the environment and to reduce cost and increase profit is to optimize the process to minimize waste. Again, we need to consider how demand translates to a supply plan to make sure that our strategy is optimal. Our approach will depend on the item attributes. Is it a slow moving item, intermittent sales? Is it a high variability item? As well as the unique organizational strategy, right? Some organizations are going to be more concerned about breaks in supply. Some are going to be more concerned about obsolescence. So it just depends on what is of the most interest to the organization. We need to consider the trade-offs of simplifying the approach versus increased accuracy. It's important to focus on the data. I mean, that's your main driver of your plan, and that includes the raw as well as the featured engineer data. I recommend starting with POCs and trying to explore and experiment with external data to evaluate the economic return. And then finally, once we have a selected approach, we need to automate and scale that as much as possible. So that concludes the presentation. Are there any questions? By the way, I have a white paper that I posted on LinkedIn that actually goes into a lot more detail about all of this.
If you have any questions, feel free to unmute and ask your question.
Comments are okay too. Reactions.
I don't have any questions. I think you did a really thorough job. Thank you.
Thank you, Peyton. I appreciate it.
Hi, this may seem like a silly question, but with a model like this you said that you use like XGB and a few other different types of, is there a specific type of model that you recommend starting out with, such as like gradient boosting or just like a simple regression, and then kind of working your way into more complex models to figure out what works best?
Yeah, that's a great question. Is that Brendan? Yeah.
Yes. Sorry, my camera's, I'm having an issue
That's
with the
okay.
camera right
That's
now.
okay. No worries. Yes, that's a good question. So in my experience, and I have quite a bit of experience in this space, the tree-based models, the random forest models, like GBRT, I have the most success with. That doesn't mean that's going to be true in every case. I have a group of students at the University of Chicago, a capstone, who are working on a real estate forecasting capstone project for me. And XG Boost turned out to be the best for them. And they looked at the same ones. They looked at ARIMA, they looked at XG Boost, GBRT, LSTM, and they got the same. Their results were based off a very different use case, different level of granularity. Housing prices is modeled more at a monthly level than a weekly level. Very, very different. But they also, their XG Boost was their best. My GBRT was the best. LSTM did not perform very well in general. And they're even talking about Gen AI and using Gen AI. I would never use Gen AI as a forecasting tool. I would use it as a tool to generate features maybe, or to use as a user interface to interact with the supply plan that is forecasted. But to get back to your actual question, so I would say start with something like a GBRT or an XG boost. Unless it's a heavily promoted item. If it's a heavily promoted item, I would maybe do something like the decomposition model or a traditional stats model to tease out the residuals. And then I would use the residuals as a target variable and model the features with that target variable using GBRT or XGBoost, something like that. If it's a brand new item with no sales, I would get a proxy item, which means an item that seems most similar. I would make any adjustments to it that I can based off of market research or personal experience. And then I would follow a similar process as what we've been discussing today, starting maybe with XGBoost, GBRT. And the goal of this presentation wasn't necessarily to say GBRT is better than LSTM or ARIMA. There's research that's already been done that's proven some of this out, but it's basically to say what gives you your best return on your investment. So I would say start with, again, XGBoost, GBRT, those types of models. Or you could use support vector regression, you could use neural nets, you could use all kinds of things, but I would start with the simpler ones that are a little bit more interpretable, depending, you don't want to use, you want to be careful about, the fact that there's autocorrelation. So that's another thing that you need to kind of be careful of. So when you're using XGBoost or GBRT, you're not modeling it the same way you're modeling a traditional time series model. You're going to, like, for example, your day of week is a feature. It's not modeled in a time series fashion. I didn't mention that, and that's really a key important point. It's modeled very differently. It's not treated as time series data.
Yeah, I understand that completely because I've worked in retail and the sales per day projected are completely different depending on the day of the week and the season and such like that.
Yeah. So that's why, you definitely want to create features that are going to capture the time dimension and potentially the space dimension as well, location. The powerful thing about a GBRT versus like a traditional ARIMA model is in a GBRT or XGBoost, you can model with, you can have location data as, each row could be a location. And that's a good thing, actually. In ARIMA, you wouldn't be, that's like multiple time series, and you'd have to have a separate ARIMA model for each location, or you'd have to model an aggregate. And that's a little bit of a limitation. So I think that's another strength of using like machine learning versus a traditional time series approach.
Awesome. Thank you so much for that.
You're welcome.
Jeanette, looks like we have one question in the chat.
Sure.
I can go ahead and read it.
Stop sharing and look at the chat. Or...
I can go ahead and read it for you. Hi, greetings, Professor.
Okay.
Touch upon the confidence interval methodology to capture uncertainty in demand forecast for estimating range of aging inventory. Is that an important consideration?
Absolutely. You can use Bayesian models there are applications with probabilistic modeling that you can use in forecasting. In fact, I use it. I've brought it into my supply chain optimization course. The last time I taught the course in spring, which was when it was last offered, I co-teach it with Gazem. We had a really small class, so we had time in the last module to actually do some supplemental material, and I did do some presentation on using a Bayesian approach. Now, you're talking specifically about aging product. Are you saying like to forecast the likelihood of the extent to which it'll age? I'm not sure I totally got that part of it. Feel free to jump in. So, I mean, it's risk, right? You're saying if the product ages out, it's risk. So you're trying to understand, like, what is the probability? What is the credibility interval for that product aging out? Do we expect it to age out, you know, in a month, in 5 weeks, 6 weeks? I'm not 100% sure I'm answering your question, so I'm sorry if I'm not.
They said yes for perishable products such as cereal, for instance.
Okay. Yeah, so I mean, you could use that to kind of get a sense for what your waste is going to be. And then I think it'd be really hard to actually plan off of a probabilistic model in the future to say what will happen from an aging perspective. But I suppose you could incorporate that into your assumptions and build your, you know, a risk mitigation around sorry, it's been a long day, a risk mitigation plan around that. If you want to talk offline, feel free to message me in LinkedIn and maybe I can do a better job of answering your specific question.
They said, thank you, Professor. I will reach out to you. Thank you for your question.
Okay, perfect.
Any more questions?
Hi, hi, I have a question. I wanted to get a view on, sorry, thank you for your presentation. It was very insightful. So I wanted to get your view on, you know, there's an advancement in machine learning and how, and we require a lot of feature engineering. And do you think as machine learning advances, the need to do feature engineering would decline, for example? So I wanted to get your view on the relationship between those two.
Yeah, that's a great question. The short answer is yes. I don't think it'll go away. There's going to be business knowledge that you will bring to the table that I don't think the automated machine learning will completely eliminate. I know, you know, if you think about the advances that we have, a lot of them are around hyperparameter tuning. They're around monitoring the models when they're in production, and all that is incredibly helpful. From a feature engineering standpoint, I don't think it's as mature as it is on the hyperparameter tuning and on the monitoring side, but I do think there is still room for it to become more mature and to automate even more of that feature engineering. But there is an art, like in my white paper, I specifically say it's a combination of an art and a science. We want to automate as much of this as possible, but there still is going to be some domain expertise, business expertise that's going to come into play. And that's going to be particularly important on the feature engineering side.
Yeah, I agree. Like, I think at my work, I spend a lot of time like doing feature engineering, and that can sometimes heavily change the model performance. So yeah, thank you for your insight. Yeah.
You're welcome, Julie. And I think the feature engineering, depending on how loosely you define that term, some people would consider transformations as feature engineering. I'm not sure I love that, but you know, for example, standardizing your variables, creating, you know, z-scores or whatever, and you know, a lot of the data cleaning and transformations, if we can automate as much of that as possible, that's fantastic, because I know none of us love that, right? Let's automate the heck out of the data cleaning and all of that. But truly understanding how to make more data with the data you have and make it meaningful is, I think, going to be a skill set that we're going to need for a long time coming.
Yeah, and thank you for your answer. Sorry, if I can ask one more question, I think. So like we mentioned, like you were just talking about how, you know, maybe we don't have enough data and sometimes we need more data, and that's where feature engineer also plays an important role. And what's your advice on, say, like your data is not in a good quality, or you have very skewed data, or really you don't have enough data? Like, how do you come about with that?
So those are very different scenarios. If you don't have enough data, you know, obviously creating synthetic data is a good option. there are a lot of options. There are a lot of, you know, ways that you can do that. Synthetic data vault is one. The quality of the data is difficult because if you don't know what the ground truth is, you don't know how to manipulate that data. You don't know what to do with the data to make it better. I think, you know, obviously that's a tough place to be in. But in general, I think you can, like, I'll give you an example. When we were looking at a pricing model, we never had a situation where, you know, the pricing was so low, right? Or where the pricing was so high. So the tails of that were hard. We had to kind of generate synthetic data to sort of mimic what those tails would look like in a distribution, because we're never going to pay somebody to do the work, right? They're going to pay us. So you know, there's certain times where you don't necessarily have the full scale of what you need in the data, and synthetic data, you know, was created to be used in a model. So I think that's probably in most cases going to be the direction you'll want to go.
I see. Yeah, thank you. Thank you so much. Sorry, a lot of random questions.
Okay. Any other final questions?
Hi. Yeah, I have, sorry, one question. Well, first of all, thank you for the presentation. But what I was going to ask is, like, now that we have social media and there are people like kind of do like product reviews and talk about that, and how important is that kind of organic media to the demand of a product?
That's a really good question. I think it can be critically important. It's definitely important from a retrospective standpoint, right? Because it can explain things. It may not be predictive, but it can explain differences in sales, right? But you know, an example would be if there was, let's say, hypothetically speaking, mad cow disease or something like that, right? If we're monitoring in real time people's response to that, that might signal to us what that could do to a food supply chain that procures beef, right? If there's like barely any buzz, we might not assume that people are freaking out, and we may continue with our regular production. If people are freaking out and there's all this stuff on social media about it, then we might want to significantly reduce our production. And so I think that can be used in real time to make decisions about supply chain. But I think in most cases, the utility is going to be retrospective and helping to explain versus predict in real time. I'm sorry? Alberto, I don't hear you. You're on mute now.
No, nothing. Sorry.
Did that answer your question?
Yeah, thank you.
Other questions? I know we're pretty much at time. I'm okay. I don't know.
Yeah, feel free to jump on and ask your question. Oh, we got one question in the chat. Hi, Professor. During my role, we encountered an issue where the POC and the A/B testing results were promising, yet the official deployment yielded significantly poorer performance. One possible explanation I considered was that the testing environment might have not fully captured our real-world conditions. Would you have any recommendations on how we might optimize or adjust our approach to better address the discrepancy?
Yeah, I mean, that can happen. That does happen. So there's a couple things that could have happened. The hypothesis you presented is definitely a viable hypothesis. Another one is because you're looking at static data in a lab environment in most cases, and you're dealing with real-time, you know, rapidly changing data in production. We always want to assume degradation of the model when we go to production. I don't know what that percentage is necessarily, but we always want to assume whatever we're seeing in a lab is your best case scenario. Okay. So if you just barely met your metric in the lab, when you, and in A/B testing, you might miss the mark in production. So you want to set your benchmark a little higher in the lab than what you need to achieve in production. That's like the first thing. The relationships change, and they can change quickly depending on the business. And so your model might be obsolete by the time you put it into production, unfortunately, because it takes time to put a model into production. All right, so that's another thing. So stale data is one, changing business environment is another. But yeah, I don't know that I have too much more to say on that. I would definitely try to, I mean, in general, when you're doing something in a lab environment, you want to build it, you want to prototype it as close to the environment that you would productionalize it in. So if you're using, Databricks on top of Azure, for example, and you I don't know, ML Flow and whatever you're using for orchestration, like however you're doing it in a lab without going crazy, right? Should match the environment that you're going to deploy in as much as possible.
All right, I think we're 5 minutes over our time. We'll go ahead and end it here. Since we don't really have any more questions, I do want to make sure that we give a round of applause to Jeanette for her wonderful talk, and thank you so much for spending the afternoon, or no, we're in the evening now, with our data science community. Also, I want to say thank you to everyone on the call. We look forward to having you all again joining us in our next seminar set for January, so the new year. Yeah, have a good night and take care. Jenna, anything you'd like to say before we sign off?
No, other than thank you.